Very sorry, I have to start with an apology, but I'm not Fuad, obviously, I'm James. And this is a bit of a last-minute presentation that I stepped in to fill in the gap in the slot button. So the title of this is Statistical Analysis of Effective Diffusivity Estimations in Porous Media, which doesn't sound that exciting. But really what I'm trying to do here is prove to you that, contrary to popular opinion, size does matter. And that's what I'm going to be trying to explain throughout this presentation. So as a brief overview of what I'm going to be talking about, I'll start with an introduction to diamond light source, and I think this stems from some of the conversations I've been having over the last few days. So I'll give you an idea about the different beamlines we have available, the different techniques, and then also how you can access them as part of the proposal system. Then I'm going to give you a bit of my own background, which links to IBSim and Cleon, and how I ended up working at Diamond. I think it's a nice example of how the community has been working together. And then I'm going to give you an example use case of why I want to develop these types of stochastic tools. And then finally talk about the development of this type of representative elementary volume calculator. So what is Diamond? So Diamond is the UK's national synchrotron. You can see an image of that at the top left. So this is a giant, a large 500-meter circumference synchrotron facility, which accelerates electrons close to the speed of light. And we do that using this linear accelerator in the center here, which is an electron gun, which fires them out at approximately 99.9% of the speed of light. They then come into this booster ring where they're boosted by a series of pillboxes and vacuum tubes to get it up to very, very close to the speed of light. And then finally, they come out into the storage ring on the outside, which is the facility you can see here. And then we have a series of different magnets, which we can then extract and energize the electrons into X-rays. And we use those X-rays to do lots of different types of experiments. And we can either do that using bending magnets, and you'll see the beam lines indicated by those, or insertion devices. And this, trust me, this is a technical term called a Wiggler magnet. But this is for the I beam lines. And you can see that we've got 34 different beam lines surrounding this ring, all doing different types of science in different scientific areas. And the beam lines that I work with are the different imaging beam lines. And we saw in Professor Phil Wives's talk earlier, talking about I-13. And you can see we've got this range of different beam lines, all doing different image techniques. And I think it's quite intimidating when you first come to Diamond. You can see all these different beam lines, all the different codes. They're not named that, obviously. And so what I've been trying to do in the last day is trying to address them in a more approachable manner. So what I've done is plotted them in terms of length scale on the y-axis. You can see from going from bulk measurements down to atomic level. And then on the x-axis, we've got this time. And this is really where the synchrotron techniques come in, where you can try and capture these different operando measurements. And you can see I've got different colors for the different beam lines. So I-13, the one that Phil presented earlier this morning, this is where we've got geometric magnification. You can see that gets down to close to the nano level. And depending on different techniques, whether you're doing 2D radiographs or 3D tomographs, you can do captures either milliseconds or up to the minute level. And you can add in I-12, which is higher energy performance, where you can get to larger specimens. Diad, where I've been previously doing my postdoc, combined imaging and diffraction. I-11, where you do powder diffraction, I-14, which is the nanoprobe beamline, and finally EPSIC, which is our series of TEM machines. And so you can see we start to build this big spatial correlation picture of how we can probe different length scales and also different time scales across the different scientific use cases. Oh, sorry, do you want to take a picture? And I can share this afterwards if you're interested. So I think this is just a useful resource to give to the community because we don't know if we've got this before. So in terms of access to Diamond, you can apply. We've got a bi-yearly application period. We're currently running up to AP34. We just had one in the last month. So you can see you can apply for standard proposal time in March next year or October. And this is free at point of use. So you can apply and put together a proposal, and we'll pay for your hotel and your travel as well, and also your costs for food. And you can come and use the beamline to do your scientific experiments. And a proposal is not that extensive. It's a 2 A4 page proposal. You can see it's made up of an abstract where you talk about the general scientific context. You then describe the scientific case you're trying to use and why using synchrotron radiation is important. Maybe it's the operando nature, maybe it's the different length scales. And then finally, you describe the experiment proposed, so what type of beam energy you want to use, what type of spatial resolution, and where you're expecting to publish. And so in terms of route to beam time, this is what we try and recommend. You maybe come up with a different idea of what an experiment you want to do. You then contact your local beamline representative, maybe myself or someone else at Diamond. And we try and help you prepare that proposal. So we try and make you put together something that's technically feasible. It's got capabilities we've already got in place at Diamond, maybe some kind of in situ testing rig, or the different energies required. And then finally, it goes for a technical review. You submit it. It goes for a technical review. It's checked by the Beamline staff, whether it's possible. Hopefully it passes that stage. It then goes to a peer review panel where it's chosen by a series of different academics and scientists from different scientific backgrounds. And then hopefully you get allocated beam time. If at any point you're unsuccessful, we'll then give you feedback about the proposal, and then you can apply at the next allocation period. So this isn't any lost time here. You can still then refine those proposals and put in more beam time applications. And this is following on from Phil and Cleon's message about data science and how we're going to be open accessing this data. And this is something I just thought of earlier. So this is a large scale pan-EU network of different synchrotrons and beamlines and different data analysis facilities that are coming together to try and solve this problem. So this is quite a large scale funding program. Diamond is involved, and I believe we've got some funding available if you're interested in this type of open access data, but it's all about trying to standardize data repositories and making them accessible. So if you're interested in that, I recommend visiting Expands. It's not my program, but it's just something I heard about at work, which you might be interested in. So some of my own background. This is kind of following on from Lionel's talk about adaptive mesh refinement grids. This is something similar I did during my PhD. And really, this is a summary of what I did in a slide. So over 4 years, I would make some type of electrode material. So this is looking at lithium iron phosphate battery. I would image that using X-ray CT in the MUPhys department where Thomas works. Do some kind of segmentation, reconstruction to get a two-phase image in this case, and then use that as the basis for an image-based model. And similar to Lionel, I developed a piece of open source software. So this is a voxel-based solver. It uses finite differences. It can be parallelized. It can run on MPI, InfiniBand, containerization. And the whole point is you can deploy it to different HPC structures to be able to do these types of simulations. And the whole point of all those different acronyms and words I just said in terms of computing is that it runs very fast. So this speed on the bottom left graph you can see here, the y-axis is the time taken to arrive to a solution. X-axis is the number of computing cores. As we move to left or right, we've got a much bigger computer, a supercomputer. And you can see that with these typical tomography sizes you get from data sets, you can solve data sets in a few minutes, which makes it much more accessible for simulation times. Okay, what's the point of all those, that speed increase? It unlocks a few different things. One, you can start to use it to validate REV, which is what I'm going to be talking about today. You can also start to look at operando simulation results, which for beamline scientists is very exciting. We could use this as a platform for multi-physics development, adding more physics. At the moment, this is just looking at steady state Laplacian type problems. Or indeed, you could use it for some type of high throughput optimization where you digitally modify images, maybe using erosion dilation techniques to develop a series of images, and then brute force your way through them to work out different parameters. So I came to present that work a few years ago at IBSim, and I met Ollie, you can see in the audience, and did a talk yesterday. And he was also interested in doing this type of voxel-based simulation. He'd been developing servos. So he approached one of his colleagues, and they were interested in developing this type of automated pipeline you can see here. So do some type of X-ray tomography measurement, reconstruct it using their in-house Python package called Savu, do some machine learning, convolutional neural network-based segmentation, and then use that as the basis for image-based model. And the whole point of this is to deliver an automated pseudo real-time data processing pipeline. The idea is you would come to the beamline, perform some sort of in situ experiment, and get your data analysis while you're still on site. And the whole idea is that you're informing the experimentalists while they're still there, and then they can start to inform their experimental procedure. Maybe they want to change the spot size of the diffraction beam, the spatial resolution, whatever they're interested in, to deliver that. So this is what I did in my previous postdoc in the last couple of years, delivering this type of pipeline. We use something called Zocalo. And if you're interested in that, please contact me. Because really we could drop in any type of simulation software here, as long as it's voxel based or maybe a different type of mesh based system. And what I really wanted to do is deliver this paper writing tool in a box, a button you can click which should deliver different visualization plots. And maybe that was a bit too ambitious because this doesn't quite work. So this is a Jupyter Notebooks plotting scheme where you could choose different visualization methods, different simulation things. And then you could plot this directly to users while they're still on site. So this can be deployed on HPC infrastructure and currently uses YT, but yeah, uses .vtk data viz system. So PowerView, anything else that you're interested in using. And while I was working at Diamond, I also got involved in the beamline science. And so this is one of the beamlines I started working at. This is the dual imaging diffraction beamline. You can see what this actually looks like. It's quite a large room, all lead lined. Involves this big robot, which can be quite scary at nighttime. This is a diffraction detector you can see on the end, a PCO imaging detector, and X-rays coming from the left-hand side to perform some kind of characterization technique. And so what does that mean? So basically we can perform a radiograph, so you can see here similar to what we saw previously in the other talks, but we can also drive our diffraction beam to perform phase characterization within that 2D space. So you can see these three different positions, 1, 2, and 3, and I've directed the diffraction beam to perform those different phase characterizations of the crystal structure. So you can see these in the tomographic reconstruction from 1, 2, and 3, coming through the different materials. And then when we reconstruct that 1D diffraction pattern, we can then use that to characterize the material. And when you combine that with imaging, it suddenly gives you more information. Suddenly we're not just characterizing material based on grayscale value, we're also doing this based on the crystal structure. And if indeed you're looking at strain measurements, like Fatih was talking about, then you can also use that to characterize how the strain is changing in the crystal structure. So what do we want to get to? We want to get to a point where we can correlate these different multimodal data sets together. And you can see that pipeline similar to what I was talking about previously, where we combine that with our X-ray diffraction measurements. We might have some type of data reduction, some peak fitting through Jupyter, to then combine that together into some form of image-based simulation. And I've put together a bunch of packages, but this could be Amitech, this could be OpenImpala, COMSOL, maybe not COMSOL because that's quite slow, but or Phoenix or something. We're quite agnostic towards the simulation package. But this type of multimodal simulation is really important to Diamond. So what might that look like? And I've got an example of this type of multimodal data. You can see here, this is from Johar Eljak's work and Phoebe Allen. So these types of zeolites, this is a type of luminosilicate you can see here. The typical formation is this mordanite, it forms in volcanic ash. But gizmodine is this very high value product because it can extract cesium from nuclear waste. So we're interested in converting it from mordanite into this gizmodine, and they've got a different manufacturing process. So they came in and did some measurements. You can see here tomography and also diffraction and the constructions of the sinograms over here. And what we wanted to do is use the information from both the tomography and the diffraction data to combine it together to give us more data. So you can see here the grayscale values of a 2D slice through that structure. And when we combine that with the diffraction measurements, and you can see the different positions of this around the data set, we can then start to identify the different crystal structure, and we can then characterize the gizmodine and mordanite phase. And we can actually then see that this was formed on the surface. Maybe we could change the manufacturing method, form the pellets to be smaller or something like that. And so what's life like as a postdoc at Diamond? You can see all these different types of science. Obviously, I started in electrochemistry on the left-hand side here, but I've been working in lots of other different fields. So people bring me different exciting specimens. I look at soil mechanics, I look at catalysis, this is zeolites again, biomechanics, meteorite systems that landed on someone's driveway in Suffolk, which was quite an exciting project, additive manufacturing and metallics. And just to say that obviously this work involves a huge amount of people from Diamond. You can see Ollie King's name at the top left, just to give you the respect. And so yeah, that's what my life is like at Diamond. And if you're interested in any of that, please get in touch. But to get on to the science, okay, so this, how much time do I have left? Perfect, okay. So this is a beam time I did previously, looking at the compression of an aqueous aluminium-ion battery. So this is a very early TRL level battery, very low life cycle analysis. You can see in the center here some SEM images of the electrode structure. This is TiO2, this is copper hexacyanoferrite, a type of blue paint. And then the electrolyte is actually made out of deodorants. This is very low life cycle analysis, environmentally recyclable and low impact. And they typically use these types of carbon felts as the electrode structure. So on the left-hand side, you can see this fibrous formation. And the trouble is the electrical conduction is linked to the connection of these different fibers. So typically what the electrochemists do is they squash these things to get more conduction. What that does is it closes off the pore space involved in this structure. And that's how the ions are diffusing through. So you've got this interplay between electrical conduction and ionic diffusion in these two different phases. And what we're interested in doing is trying to characterize that. So we went away and constructed this in situ testing rig. You can see here, 3D printed, this is version 1 of this guy, and took it away to the beamline to do some nanoscale tomography. Or maybe it's 330 nanometers pixel resolution, still not quite nanoscale. But you can see on the left-hand side, this reconstruction of 2D slice, uncompressed, right-hand side compressed, you can see that pore space is closed off. And what I wanted to do is characterize how that pore space had changed as a function of that. So this is a perfect case for image-based modeling, except I had 11 different load cases of these two different load samples in between here. And then I also had 12 different samples. And that, once I did all the reconstructions, there's about 20 terabytes worth of data, all captured at synchrotron resolution. And it was going to be a data nightmare to try and process it all. And so instead of trying to do that, well, actually, first you can see some segmentations. This is using Ollie's serval space package. You can see drawing on these different positions, doing the neural net segmentation, reconstructing that into a 3D volume. You can see uncompressed on the left, right-hand side, you can see it compressed, closing off that pore space. And then you can do some type of simulation. So this is looking at concentration flow using OpenImpala. And it does what you expect. So as you squash it, concentration goes down, conduction goes up. But the point was, and to say acknowledgements to all my collaborators. So this was University of Southampton Imperial College, and some of the synchrotron stuff was done at BSI. So thank you to them. So that brought me on to how was I going to analyze this different data and how I could do that more efficiently. And so that came into the idea of doing this type of REV calculator. How big is big enough? And this is the point of the presentation. So I modified the boundary conditions. I was using an OpenImpala, you can see here. We go from a flow through type geometry into a more homogenized process. And this is more characteristic of ion transport inside batteries. You don't capture blocked pores using that left-hand side simulation package. And there's a great paper by Sam Cooper, who Phil mentioned earlier. But this involves having to do periodic boundary conditions. You can see as you have to move from the left-hand side to the right-hand side, so it involved having to change the code. It's all written in Fortran. I don't really have much time anymore to do that kind of coding, but yeah, found some time one weekend. And you can see what the type of simulations would look like. So you start with a large scale image domain on that left-hand side. This is looking at soil mechanics in this particular instance. We then extract a smaller subvolume. In this case, I think it was 2 millimeters, you can see here. And we're trying to work out this homogenization problem. How big of a cube is big enough to represent this volume? And for each different system we look at, you think back to those different science cases, catalysis, soil science, electrochemistry. We have to do this computation each time. It's going to be parameter dependent, it's going to be size dependent, it's going to be characterization technique dependent. And I wanted to develop this type of technique where you could then bring this to the beamline and perform that characterization quickly. So what I then do is extract from that subvolume a series of different increasingly sized REVs. So you can see here on that left-hand side, we go from 31.31 millimeters up to 2 millimeters. And I also then seed 10 different randomized seed points from within that volume. And I grow all of those 10 different stochastic volumes. And the point what I'm doing here is I'm brute forcing my way through the parameter problem. So you end up with the graph looking something like this. So effective diffusivity is plotted on our y-axis. X-axis is that length scale. We're going from small cube on the left-hand side to big cube on the right-hand side. And I'm plotting in the 3 different Cartesian directions. This does do a 9-point tensor, but I'm just plotting this for the sake of ease. And you can see what you expect to happen. So as you increase your length scale of your block REV size, you then get much smaller uncertainty, and you start to get down to a much more repeatable solution. And I think this is a really important message, because typically what I see at image-based modeling conferences is people come in and do one simulation, but actually when you look at taking different volumes within your domain, it really changes the result you get. And yeah, I think this idea of stochastic representation is very important and will improve models in terms of robustability and actually the features and parameters we're getting within our different domains. So thank you to my collaborator again now at Southampton, so Tina Roos and her team, who are involved in image-based modeling of soil mechanics. And I think I just leave you with that slide. Firstly, so use your local synchrotron, hopefully Diamond, but please use any of them because I think they're exciting facilities. And you do get a very good buzz from doing late night science where you stay up late using these big machines. Thank you to Cleon and IBSim, especially for my current job, because it's great. And I'm very interested in collaborating, especially in beamline tools. So if you're interested in that, please get in contact. My email's up there. Thank you very much.